We'll look here now at p-values. It's a part of inferential statistics that students, they rarely enjoy it at the start, but once you do enough of them, you kind of find that they're actually not that much more difficult than getting the z-score, the test statistic, because it's just another step on from that. So I'm going to read a little bit of theory here at the start, okay? So stick with it for the first minute, right? Because after that, when you see the examples, it does get easier and make more sense. So, okay, we have one more method of hypothesis testing on our course. This involves finding the p-values. The p-values are the probability values. So they tell you how likely it is that your data could have occurred under the null hypothesis. It does this by calculating the likelihood of your z-score, your test statistic. The p-value tells us how often you would expect to see the test statistic as large or larger than the one calculated by the test if the null hypothesis of that test was actually true. Okay, so that sounds a bit tricky, but we'll see how to do it now in a moment. The p-value is a proportion. Okay, so if your p-value is 0.05, this means that in 5% of the time you would see a test statistic at least as large as the one you found if the null hypothesis was in fact true. If the p-value is smaller than the significance level, we reject the null hypothesis and accept the alternate hypothesis. So again, there's your theory, right? So let's look at an example. Suppose we carry out a hypothesis test and we find that the test statistic is z equals 2.16. Now here's the truth. Once you have a z-score of 2.16 and you compare with 1.96, we could say, well, since z equals 2.16 is greater than 1.96, we reject the null hypothesis at the 5% level of significance. Okay, alpha is equal to 0.05. But instead of comparing z equals 2.16, okay, with z equals 1.96, so instead of that comparison, what we do is we compare the total area inside the coloured regions below. So to the right of plus 2.16 and to the left of minus 2.16. And we get that number. And in that case, we're going to compare that number with 5%, 0.05. Okay? And the smaller that number is, the more significant you're finding and the more likely you are to reject the null hypothesis. So we use page 36 and 37 of the Formula and Tables book to find the probability that in this particular case, like what we're talking about, is z being less than 1.26 and z being greater than plus 2.16. Those are the numbers we're talking about. So it's highlighted, they're the ones in the highlighted area above. Okay, because the probability of z being less than or equal to minus 2.16 is the same as the probability of z being greater than plus 2.16, all we do is find the probability of z being greater than 2.16 and double it. So we just find this region over here that's in blue as we look at it there, and we double it. Okay, we know of course already that we can't just read from the table book the probability of z-score being greater than 2.16. So instead we find the probability of z being less than 2.16 and take it away from 1, the full area. We find in the table book that the probability of a z-score being less than or equal to 2.16 is 0.9846. Take that away from 1 and you get 0.0154. You double it to get a p-value of 0.308. Okay, so that is less than 5%. So basically that'd be 1.5% of the area under the bell curve is over there, and there's another 1.5% of the area under the bell curve is to the left of minus 2.16. So the shaded area is referred to as the p-value, the probability value corresponding to the observed value of the test statistic. The value of 0.0308 found is the p-value that corresponds to the test statistic of the modulus 2.16. The p-value is interpreted as the lowest level of significance at which the null hypothesis could be rejected. With the test statistic of z equals 2.16, we certainly would have rejected the null hypothesis at the specified level of significance, 0.05, or comparing it with z equals 1.96. The p-value of 0.0308 gives us a specific or more precise level of significance. The smaller the p-value is, the stronger the evidence against the null hypothesis provided by the data. Now, again, somebody looking at that will be thinking, whoa, that's a bit much, right? But let's go through it. So let's go through it again. And once someone said to me recently, you got to learn statistics twice. You got to learn it once, like incrementally, bit by bit, from the theory to the end. And then you got to learn it again after that, just when you're doing examples and so on. And all of a sudden, they can come together then. So let's hope that's the case in the next 2 minutes. So what do we do to get the p-value? We write down the null hypothesis and the alternate hypothesis. We calculate the test statistic, which is your z-score. We find the p-value that corresponds to this test statistic. If the p-value is greater than 0.05, the result is not significant, and we do not reject the null hypothesis. But if it is less than or equal to 0.05, we reject the null hypothesis in favor of the alternate hypothesis. So example 7. In a random sample of 36 observations to be taken from a distribution with standard deviation of 10, so n is going to be 36, and sigma is going to be 10. In the past, the distribution has had a mean of 83, so that's mu, my historical mean. It is believed that the mean may have changed. When the sample was taken, we were found to have, the sample was going to have a mean of 86.2. What we do is we state the null and alternate hypothesis. Now, even though, this is a great example here, even though it is believed that the mean may have changed, even though that is the case, the null hypothesis is the hypothesis of no change, that it is the same, that mu is equal to 83. The alternate hypothesis is there is a change, so H1 is that mu is not equal to 83. The test statistic, z is equal to x bar minus mu all over sigma over root n. So x bar is 86.2. That is my sample mean. Minus mu, which is 83, my historical mean, all over sigma over root n. My standard deviation divided by the square root of the sample size is equal to 1.92. Now here's the thing. You can make your conclusion. If you're inside in the exam and you forgot how to do p-values, you could make your conclusion to your hypothesis test just from that, because that number is less than 1.96, so therefore it's not significant. However, to calculate our p-value, we're comparing with greater than and less than 1.96. So what we're doing is we're comparing with 5%. So what we do is we're going to find the probability of having a z-score greater than 1.92. We're going to double that then, because that will get us the two ends of the bell curve. Okay, to the right of 1.92 and to the left of minus 1.92. Okay, so I work out the probability of the z-score being less than 1.92. That works out to be 0.9726. And that's everything to the left of that line there, all the way over, including the tail over here. I take that away from 1, and that gives me the little tail in on the right hand side. It's 0.0274. I multiply that by 2 to get the two tails, 0.0548. That number is my p-value. It is greater than 0.05. The p-value is not less than or equal to 0.05. The result is not significant. We do not reject the null hypothesis. There we go. In less than 10 minutes, you've done the p-values. I hope it makes sense to you now. And when you see a few more examples and practice a few more of it, you're going to see that it's not as hard as maybe one would think at the start and when you read the theory. Okay, we'll see you again.